Hello and welcome to this Python tutorial. So we just initialized our convolutional neural network as a sequence of layers using the sequential class, and now we're about to add the first layer of our CNN. But before we add this first layer, let's just give us a quick reminder of the building process of the convolutional neural network, which is right here on this slide. So the CNN building process takes 4 steps. Step 1, convolution. Step 2, max pooling. Step 3, flattening. And step 4, full connection. And in this tutorial, we will take care of the first step, convolution. So let's also give us a quick reminder of what this convolution step is about. So we have an input image. In our case, the input image will be the image of a cat or a dog. But here on the example of this slide, this is the input image of a smiling face. We converted the smiling face image into a table of pixel values, and this is what we got with all the 1 and 0 pixels. And so this convolution step consists of applying several feature detectors on this input image. So here on this slide, the feature detector is the feature detector of the left side of a smiling mouth, well, the right side, but left when we look at the person. And for each feature detector that we use, we slide it all over the input image, and when the feature detector passes over the part of the face that contains this left side of the mouth that is smiling, well, we get a high number in this table on the right, and this table is the feature map. So for each feature detector that we apply on the input image, we get a feature map. The feature map contains some numbers, and the highest numbers of the feature map is where the feature detector could detect a specific feature in the input image. Alright, and that is the convolution operation. This operation here between the input image and the feature detector that results in a feature map is the convolution operation. And so we do this with many feature detectors. We will choose in this first convolution step the number of feature detectors that we create, and therefore the number of feature maps, because we get as many feature maps as feature detectors we use to detect some specific features in the input image. And therefore, eventually, we get our first step convolution done. As soon as we create these many feature maps, that will form our convolutional layer. And that is exactly what we're going to build here, the convolutional layer composed of all these feature maps. So let's do it. It's actually going to take one line because we already imported the packet that we're going to use to add this convolutional layer. And so this is going to take one line, and we are going to start this line by taking our classifier because, of course, this is an object, and we're going to apply a method on this object, which will be nothing else than the add method that we already used to add a layer, but it was not a convolutional layer, but a classic layer composed of several nodes. That's what we did in the previous section, building the ANN. But here, some things are of course going to change. So let's take our classifier. Here we go, paste, and then dot to introduce the method. And here we go, that's the method we want to use, add, pressing enter. And now parenthesis, and in these parentheses we will add the parameters of our convolutional layer. So now remember, when we added the classic layer in the ANN section, what we used here was the dense function, but this dense function is used to add a fully connected layer like in the ANN, and therefore this is not the function that we're going to use here. The function that we're going to use, you can guess what it is convolution 2D. And we can use this function thanks to this import here, convolution 2D. Alright, so now new parenthesis, and let's see what we need to input here in this convolution 2D function. Alright, so I'm going to press here Command I to get some info about this convolution 2D function, and here we go. So we have several arguments, as you can see here, 64, 33, border mode, input shape. So let's see what they are. Alright, so the first argument is NB filter, the number of filters. So this is exactly the number of feature detectors that we're going to apply on our input image to get this same number of feature maps. So the number of filters that we choose here is the number of feature maps that we want to create as well, because there will be one feature map created for each filter used. Alright, so we need to choose this number of feature detectors, but that's not the only thing that we need to choose here. As you can see, okay, it says NB filter, number of filter, but it also says number of rows in the convolution kernel. So the convolution kernel is just another name for feature detector or filter. But anyway, we have this number of rows of our feature detector and also the number of columns of our feature detector. And so to understand what it is, if we go back on the slide, Well, the number of rows is the number of rows of this feature detector table that you see in the middle of this slide. And same number of columns is the number of columns of this feature detector table that you see in the middle of this slide. So basically, if we go back to Spider, well, the numbers here that you see in the parameters of the convolution 2D function, well, 64 here is the number of filters you want to use, 3 is the number of rows of each filter, and this other 3 here is the number of columns of our feature detector. So basically, if we choose 64, 3, and 3, that means that we'll create 64 feature detectors that are going to have the dimensions 3 by 3, and that will go through the input image to create 64 feature maps. So now, what are we going to choose here for our function? Well, we're not going to choose 64 because, first of all, if you look at most of the CNN architectures, you will see that a common practice is to start with 32. We start with 32 feature detectors on the first convolutional layer, and then we add other convolutional layers with more feature detectors, like 64 and then 128 and then 256. But here, and that's the second reason, we're working on a CPU. Well, maybe some of you are working on a GPU and that's great, but if you follow the installation instruction, we are working on a CPU, so we want to start slowly. But don't worry, we'll get some very good results. At first we'll get some correct results, and then we will improve our CNN and get better results. Alright, so we are not going to choose 64 here, we're going to start with 32 feature detectors, but then we will choose these 3 by 3 dimensions for our feature detectors, and therefore we will add here 3, and 3. Alright, so that means that we create 32 feature detectors of 3 by 3 dimensions, and therefore our convolutional layer will be composed of 32 feature maps. Alright, then next argument. What is the next argument? This is border mode. So border mode, that's not the most important here. This is just to specify how the feature detectors will handle the borders of the input image, but most of the time we choose same here, that's the default value. So that's what we're going to choose here, and therefore we don't need to input it, since it will automatically take the default value. And then, very important argument, input shape. So what is input shape? That's the shape of your input image on which you are going to apply your feature detectors through the convolution operation. And that's a very important argument because all our images don't have the same size. They don't have the same format. And therefore we need to force them in some way having the same format. That means that we will convert all our images into one same single format and therefore one fixed size of the image. And we will do this conversion during the image preprocessing part, right after we build our CNN and just before we fit our CNN to our images. And therefore, in this input shape argument, we need to specify what is the expected format of our input images. That is the format into which our images will be converted. And so which format are we going to choose here? Well, first, let's go back to this slide to give us a quick reminder that input images are converted into 3D arrays if the image is a colored image, and into 2D arrays if the image is a black and white image. So here, since we are working with colored images, well, our images will be converted into 3D arrays during the image preprocessing part. And so what is this 3D array basically? Well, it is composed of 3 channels, each channel corresponding to one color, blue, green, or red. And each channel corresponds to one 2D array that contains the pixels of our images. And therefore, if we go back to Spider, well, we see that input shape has 3 arguments, 3, 256, 256. So as you might have guessed, 3 is the number of channels. So it will only be 1 if we are dealing with a black and white image, or 3 if we are dealing with a colored image. And then 256 and 256 are the dimensions of the 2D array in each of the channel. So here that means that we are expecting colored images of 256 times 256 pixels. Great, but this is not the format that we're going to use here. We're going to use a smaller format, and that is for the same reason that we're using a CPU and that we don't want to wait too many hours before the code finishes to execute. And therefore, here we're going to choose a smaller format, which will be 3 channels, because of course we want to keep these informations related to the colors, because cats and dogs don't have the same colors, and therefore differentiating them with the colors can be helpful to classify them. So we will keep the colors, and therefore we choose 3 here. But then we will choose a 64 times 64 format, because this will be way enough to get some good accuracy results. You will see in the end, If you're working on a GPU, you're welcome to choose a larger format like 128 by 128 or even 256 by 256, but you either need to use a GPU or run your code before sleeping for 8 hours. Alright, so let's input this format, but then there is one last thing that we need to be careful with here. It's the order of the input shape parameters here. As you can see, we start with the number of channels and then the dimensions of the 2D arrays. But this order of these input shape parameters is the order used in Theano backend. And here, as you can see, we're using TensorFlow backend. And the order in TensorFlow backend is not the same order as in Theano backend. This is actually the opposite order. We need to start with the 2D array's dimensions and then the number of channels. And therefore, what we need to input here for our input shape argument is input underscore shape equals, then in parentheses, first the dimensions of our 2D arrays, and therefore 64, 64, and then the number of channels, 3. And that is because we're using TensorFlow backend. So just be careful with it. Make sure that you are using TensorFlow backend if you're using this code, and if you are using Theano backend, well, just input 3, 64, and 64. Alright, and now we just have one last argument to input, which is the activation function. Exactly as we did for our fully connected layers in the artificial neural network that we built in the previous section, only here we are doing it for a different purpose. For the ANN, we used this activation function to activate the neurons in the neural network. Here we are using this activation function, which by the way will also be the rectifier activation function, but just to make sure that we don't have any negative pixel values in our feature maps. Depending on the parameters that we use for a convolution operation, we can get some negative pixels in the feature map, and we need to remove these negative pixels in order to have nonlinearity in our convolutional neural network. Because of course, classifying some images is a nonlinear problem, and so we need to have nonlinearity in our model. And that's why we use this activation function here, this rectifier activation function, to make sure we get this nonlinearity. So let's add it. It's exactly the same as what we did before. We input this activation parameter here, then equals, and then in quotes, we input the name of the rectifier function, which is, as usual, relu. Perfect, and that's done. Our convolutional layer is ready to be added in our convolutional neural network. So let's select this line and execute. Here we go, perfect. Our first convolutional layer was correctly added. So we are ready to move on to step 2, the pooling step, and that's what we'll do in the next tutorial. Until then, enjoy machine learning!